Hello and welcome. My name's Rob Watson, and with Sneha, today we're going to look at vector databases explained. Recently someone asked us, do I really need a vector database for AI, or is this just another hype cycle? And honestly, that question kind of feels like when people say, why do we need Exadata when we already have a normal Oracle database? And the truth is, you don't always need a vector database, but when you do, it transforms your system into something you didn't think was possible. When we think about how we've traditionally worked with databases, the core idea has stayed the same for a very long time. We organized information into rows and columns, we used indexes to find things quickly, and relied on proven structures that kept everything running smoothly. It gave us a solid, reliable foundation. Everyone knew how the world behaved, and it served businesses, and it still does, incredibly well. But now think about the kind of information organizations are working with more and more today. PDFs, chats, support tickets, call transcripts, website text, customer emails, entire document repositories. This can make up a bulk of a modern business's data, and it doesn't arrive in neat tables. It's free-form text, it's mixed formats, and it makes up most of what companies store and generate. Traditional relational databases handle structured values very well. They're built to match exact entries and precise fields. But this unstructured world doesn't follow those rules, and that creates a gap between the questions people want to ask and what the database can recognize. When you look across an organization, all of this unstructured material adds up fast. Product catalogs, user guides, call center logs, patient notes, large diagnostic files. The list is almost never ending, and the challenge is that traditional search tool that only works when you know the exact keywords to look for. Tags help a little, but they're usually incomplete or inconsistent. So when you have thousands of documents, each with its own style and terminology, finding the right information becomes slow and frustrating. Nobody wants to dig through 2,000 files by hand just to answer a simple question. Embedding gives us a way to translate information into a form the database can work with at scale. So we take a piece of text, or an image or audio, and convert it into a list of numbers. And that list of numbers is a vector, and it represents the meaning and context of the original context. So instead of storing only the words, we now store a numerical fingerprint of what those words are about. And with that in place, the database no longer looks for exact matches, it can look for similarity in meaning. This means it makes similarity searches very useful. You can ask the system to find the closest documents to a problem you're dealing with, even if none of the wording overlaps. The vector representation does the heavy lifting. Once information is stored as vectors, we can compare them. If two vectors sit close together, it means their content is likely to be related in context. And this simple comparison drives many AI features. It's how AI assistants understand your knowledge base, even if you phrase things differently, and how chatbots appear to remember context. To demonstrate how vector search behaves, we ran a small test in Oracle 26 AI. We loaded two short troubleshooting notes, one about video call freezing because background apps use too much bandwidth, and another about slow downloads and reducing competing traffic or moving closer to the router. And then we asked a different question. Why does my laptop struggle whenever I try to join meetings at home? None of the keywords from the notes appear in the question. There's no freeze, no bandwidth, no router or downloads. And a traditional keyword search would simply miss the connection. Vector search instead looks at the context of the question. It finds notes that relate to the same problem, even when the language is completely different. So instead of returning nothing, it brought back the two notes related to the issue. And this is the gap vector search fills. It links ideas that ordinary text searches can't. Once we start working with vectors at scale, we need a place to store them and search through them efficiently. There isn't just one kind of vector database. Different organizations use different approaches depending on their architecture and performance needs. Some platforms are purpose-built and focus only on vectors. Others add vector features into existing databases so teams can keep their current systems and toolings. And then we have the fully integrated enterprise databases where vector search sits alongside everything else: transactions, analytics, security, governance. Each approach has its strengths, and the right choice depends on what you really have in place and how tightly you want a vector search to fit within the rest of your data environment. So as we said, some databases are designed from the ground up purely for vector work, and examples of these include Pinecone, Weaviate, Milvus, Quadrant. Their main strength is focus. They optimize everything for fast similarity search, high recall, and low latency. They scale out easily and work well when an application needs to handle very large numbers of embeddings, especially in AI-heavy workloads. But there are trade-offs though. These platforms don't offer the broader relational features many systems rely on, they don't handle complex transactions or strong consistency, and they aren't meant to run traditional operational workloads. So they're great specialists, but they tend to sit alongside existing databases rather than replace them. Another common approach is adding vector capabilities to systems that are already widely used. So Postgres with PG Vector, MongoDB's Vector Search, Elasticsearch Vector features, and Redis Search all fall into this group. Here the idea is simple. Instead of adopting a brand new database, you extend the one you already have. It gives teams a quick way to start building basic retrieval augmented generation pipelines using familiar tools and workflows. That's why these extensions have been widely adopted. But again, they have limits. Because these platforms weren't originally designed for high volume vector workloads, performance can vary. They work well for smaller or mid-range solutions, but they're not usually the best fit for demanding enterprise scenarios. The third approach is full integration. Instead of adding vector capabilities as an extra layer or using a separate specialist system, the vector engine lives inside the enterprise database itself. And this is the model Oracle Database 26AI follows. It introduces native vector data types, native vector indexing such as HNSW and IVF, and built-in AI models that run directly in the database. The advantage is simplicity. Your vectors, your transactional data, your security policies, analytics, they all live in one place. Everything benefits from the same ACID guarantees and the same performance architecture that Oracle is well known for. It also means teams can use the tools they already have, SQL, PL SQL, Apex, Java, Python, whatever it is, without changing how they work. For organizations already running Oracle, this layout fits naturally into existing environments and avoids the complexity of maintaining disconnected vector systems. This is where Oracle Database 26AI really stands out. Everything stays inside one system: your data, your vectors, your indexes, your embedding, generation, and your RAG pipeline. No extra clusters, no data movement, no extra tooling to maintain. Vector search also benefits from Exadata performance features such as AI Smart Scan, fast HNSW indexing, and in-memory optimizations. It delivers strong performance even when vector workloads sit alongside transactional or analytical workloads. Security is of course unified as well. All the controls you already rely on, row-level policies, auditing, wallet integration, masking, they all apply automatically. And because the database includes built-in embedding models, you don't need external APIs or per-call charges. You can run models locally or bring your own Onyx models when needed. It gives organizations a complete integrated environment for vector search and AI without added complexity. One of the biggest advantages of Oracle 26AI is that it brings everything together in a single engine. So you run OLTP, analytics, JSON, graph, text search, spatial workload, vectors, and machine learning all side by side. There's no need to stitch together separate systems or build glue code between services. No extra operational overhead and no microservice sprawl. It gives teams one platform that can handle the full range of modern workloads, including AI, without adding complexity. And here's an example of this. One of the biggest shifts is that AI becomes part of SQL itself. You can run a similarity search with a single query, just like any other operation. Here we're asking the database to return the 5 documents closest in meaning to a given embedding. There's no separate vector service, no multi-step pipeline, and no extra infrastructure to maintain. AI becomes something you express straight in SQL, which makes it easier to build, easier to maintain, and easier to integrate with existing applications. If your organization works with unstructured information, if that information changes quickly, and if you need to search by meaning rather than by keywords, then vector search becomes essential. And for enterprises already running Oracle, Oracle 26AI offers a most straightforward path. You get vector search, embeddings, RAG workflows, AI agents, and they're all fully integrated into the databases you already trust and rely on. It keeps everything simple, secure, and scalable, which makes it not just the easiest choice, but the smartest one. As always, thank you for watching.